Welcome, everyone, to the third episode of the podcast. Thanks for tuning in. If you've come in multiple times, or welcome if it's the first time. Today, we'll share some interesting advice about people looking for careers in data science or AI. And maybe it's helpful to share some of my experiences in careers and share the types of people that Daisy hires and the types of positions that we have. And starting out is how I got into the field of AI. I think the terminology has changed a lot over the years, and really started out as kind of statistical analysis, which became data mining, which became advanced analytics, which became machine learning, which became artificial intelligence. So that terminology has evolved. I'd say faster than the technology. The technology has existed for quite a long time. So my background is in aerospace engineering from the University of Toronto. I went through the engineering science program and I did a master's degree in computational fluid dynamics. So very technical. I guess the aerospace industry, I think, has been at the pinnacle of large volumes of data and large parallel computing. So I think those skills were something that I learned in school and then I brought to the market. In Canada, there was not many aerospace industry jobs per se. And so, like many people who graduate, I didn't end up doing exactly what I went to school for. But I started to work with large companies as a consultant. My friends had a software business that we started, and I was exposed to large companies, and I found this opportunity to bring more technology to big business. I always thought these big companies that had big logos and skyscrapers were like super put together, and they certainly are. But I think in terms of application of technology, it was, I think, underserved. And I thought, not, I guess, subconsciously created this career to try to bring more math and science to business. And because I was very technical and I had these very kind of deep aerospace computational software development, parallel computing capabilities, I was attracted, and I love math. I think that's one of my skills in school. I was always very good at math, and if you talk to my university buddies, they love to make fun of me, who like to gyrate equations all the time. So I think those skills um, brought me to this opportunity of data analysis. And I found that I could apply all my skills that I learned in school. And I think that was really my motivation, to find a career where I could apply everything I learned. I really enjoyed what I did in school and I wanted to do this application. And at university, I went to Geoffrey Hinton's lectures. Geoffrey Hinton was a professor at University of Toronto, and he held many industrial seminars on neural networks and machine learning. So I attended all those and was really interested in the field. And then in the business world, I got the opportunity. I worked at the Loyalty Group, which runs the Air Miles program. At the time it was called Loyalty Group. Now it's Loyalty One. And started a consulting business there and started applying, statistical analysis, human-led statistical analysis, and got into sophisticated machine learning. And so is really this opportunity to apply my skills, and I found I was really good at it. And I found I had these deep technical skills that were rare. In university, I was surrounded by all kinds of brilliant people, and so I thought I was just an average person. And then in the business world, not everyone has the technical skills in the business world, so it was a really great opportunity. And so that's kind of how I kind of meandered into this. And I've really spent an amazing career for me doing commercial research, you know, not having any of my graduate studies skills go stale. I've continued to invest and do research and learn more and more. And so for me, it's been a very personally rewarding career of personal development and learning more and more and being able to do research and work with clients and apply the knowledge. And so that was my motivation, and that's how I got exposed to this. And back in the 90s, when I first started getting into supervised learning, I was so excited. I thought, wow, you could model anything, you could predict anything. And I think the world is kind of having a little bit of that moment now, where everyone's excited that you can build supervised learning models to predict anything. You pull these data sets and you find amazing correlations. And I think I had that kind of moment with a very small group of others at the time who were in the industry. So I think we were kind of in the early days. And then my thinking has, dramatically evolved since then, away from kind of supervised learning only. Supervised learning is certainly a very useful and powerful tool, but I think there's other ways to solve problems depending on what the problem is. So I think over the 30 years that I've been in this field, um, I think the technology has evolved gradually. Like it's not, I think, with the media hype in the last several years, you'd seem like it appears if you're not in the industry that this came out of nowhere, that it was like sudden breakthroughs. But the researchers who've been in this field, like Jeffrey Hinton, who's the godfather of neural networks, he's been working on this for, 40, 50 years, right? And so it's been a gradual evolution. So a lot of these techniques and algorithms, um, back when I was working in at Loyalty One, I would, work with a lot of university professors. They were all inventing algorithms. So algorithms were just a hot topic in the academia back in the 80s and 90s, and so all the algorithms that exist today see their precursors, and many of them are unchanged. The algorithms. So I think what has evolved is that there's been broader adoption, right, in terms of more people using these skills. I think the usability, the more programming languages like programming has become more accessible to a broader audience with the advent of languages like Python and the open source libraries. I think the open source movement has made this more accessible to non like really deep hardcore technical people. Just open source software would be software that's publicly available that anyone can get access to the source code. So typically if you buy a software product like, let's just say, Microsoft Teams that we're using today, you know when you buy Microsoft Teams, you don't get the software source code, like the actual source code that you could see. Microsoft sells you the compiled product. That's a functional product. So open source means it's a the source code is publicly available, and therefore it's co-developed by many people. So it's not necessarily one company built it. One company may have started it, released the software, and then that enables the entire population, the entire world to work on it together. And there's kind of organizations that grow around these open source projects, and multiple programmers can work on it and develop it together and add functionality. So if you could imagine, instead of having a team of 10 people build software that might be in a company, now you could have hundreds or thousands of people working on an open source project, increasing the capabilities of the software, making it available commercially free, typically, that there's no fees associated. And so that makes it easier for everyone to access the software at no cost and be able to actually code and adjust the code if they want to, or they can simply use it. You don't have to be a user. You don't have to be programming it. You can simply be a user of the technology. So we used to write our own software, back in the 80s and 90s, and there wasn't as much open source then. I think what's really pushed the industry forward is the computing power. Moore's law, which has existed, that says, basically every 18 months computing power doubles, and that's been going on for a long time, 3, 4 decades. And so, I mean, it's kind of flattened out recently because they're running into some physics limitations, hence the real interest in quantum computing. But I think the advent of more powerful computers, like my cell phone today, probably has more powerful computers then the chips are more powerful than what I did my graduate studies on when I was in graduate school, and so, I remember my thesis code used to run for 5 days. One run was 5 days. So I'd sit there for 5 days, and we created all these elaborate output from the software so we could monitor to see what it was doing. And so I would sit there and rederive my mathematical derivations over and over again. I had like 200 pages of mathematical derivations, and then I would find an error. I'd find a plus sign, should have been a minus sign. I go, oh my God, I found the bug in my code. And then I'd stop the software, change the code, go run it for 5 days again, and even before that, parallel computing for me was I had a PC at home, I had a PC at the lab, and I had a PC at my friend's house. So parallel computing was running a job on each of those three computers, and then driving to all the three locations to see how my jobs were doing, so yeah, the computing power has massively evolved. I think that's driven a lot more complex algorithms. I think the advent of deep learning, I think neural nets were really exciting in the 90s. I think people got very excited, but I think the computing power wasn't enough to train them long enough to make them useful. And I think the computing power grew so much that we were able to train larger and larger neural networks. Now it's called deep learning. Deep learning is just very large, multi-layered neural networks, and that's allowed a lot of advancement in practical application. So there's been a lot more, so I'd say open source code, more easily accessible programming languages, lots of mathematical libraries, and the increase in computing power has brought more and more practitioners into the industry than there were. It was a much smaller audience back when I started. I think it was because it was a lot more, the barrier to entry was deeper technical than it is today, which is a good thing. The more people in the industry, the better. The more evolution, more people working on it, more brains, all of that stuff. So I'd say that's how it's changed. I think with the advent of all the people in the field now, I think that's what's created this hype. I think it's the volume of activity is what's driven this media hype, but the number of people participating and therefore the number of companies exposed and the interest is larger just because there's a much, much larger population of people working on this today. And so just talking about technical skills and background people might need, um, to succeed in this industry. So I think there's many career paths. Some could be deep technical. So I think if you were to go to the most technical route, which would be writing AI software using complex languages like C or C++, which is the base language that many of these open source projects or products that are written in. So that would require kind of a deep technical education. So that would be people with degrees in STEM would be typically, computer science or mathematics or engineering. I'm partial to engineering graduates and the very technical side. I think engineers have a broader education. And for me, that's important given the branch of AI we're doing, which when I talked about the theory of approach and differential equations, I think it's a bit of a combination of mathematics, computer programming, the physical sciences, and I think engineers get all three of those in very balanced measure in their education, whereas I think computer scientists maybe are missing some of the physical sciences like physics and chemistry and those things. That's not necessarily a part of a typical computer science curriculum. Um, and the computer scientists maybe don't get as much mathematics as some of the engineering programs do. And then on the flip side, mathematics students get a lot of math. They don't get so much physical sciences. They get they get some less computer science and computer programming. So, but I think though any of those three are career paths, and certainly if it's not a formalized program, a computer science student could take physical sciences. It's like more of a major as opposed to engineering. It's a really kind of laid out curriculum where you don't have a lot of flexibility and choice. But if you're taking computer science or mathematics, you have a lot of flexibility in what courses you could take. So I would suggest anybody going the technical route will try to take a bit of a balance of those three things, as well as databases. I think having database skills is great, and then some mathematical skills because a lot of these algorithms are deeply mathematical, and then some physical sciences because those are a lot of useful analogies come from the physical sciences that get implemented algorithms. So that's one path, deep technical um, path. And I think even if you don't choose to go the deep technical route, having some level of that technical education, if you want to call yourself a data scientist or an AI user, so somebody who might be working in a company doing analysis using tools that the company bought or open source. I think that would come from that kind of STEM, scientific, technology, engineering, and math background. So I think that's an area. And so really deep technical people, maybe with graduate degrees, would go pursue building the technology, working in research labs, maybe being the most technical people in a company, maybe working for tech companies, getting maybe undergraduate degrees in STEM. That would be, you could become data scientists in companies and applying, being an applier of the technology. I think, that's there. And then I think there's a lot of, I think, business analysis, I think, and consulting. I think that's a whole other area that could be less technical, but equally as important. As I talked about in the last episode, was all the change management. So change is a huge part of this industry and will be. So I think having consulting skills, having a little bit of technical background, so you kind of have at least a base level understanding of the technology. At Daisy, our customer success people are people who have analytical skills, who also meet with our customers and talk to the customers and translate the technical findings. I think that's a whole area. So I'd say deep technical, data scientists, a little less technical, with just undergraduate degrees. The deep technical ones could be, with graduate degrees. Then, the customer success people being consultants, maybe a bit of business, bit of analytics, people in kind of business analytics program. There's a lot of people who do that as an educational path, or applications. So defining the interfaces to the software as a whole career, that tends to be technical people as well who go through web development. And then operations, people running the software. We have an operations team at Daisy that runs our autonomous machines, schedules data jobs, um, to run our computational jobs, our data pipelines, our machine learning pipelines are all run by operators. So there's technical operators who do that. So I think the deeper the education, the more technical the role that you could take on. But there's fewer deep technical roles than there are more application or user using the technology roles. There's much more of those types of roles out there. There's not many companies that are necessarily building original technology. I like to think Daisy's one of the few. We built our own technology and don't use open source projects or off the shelf tools for our machine learning or reinforcement learning software that we've built. Has been all our own homegrown C++ parallel computing for NVIDIA GPUs. I think, what do I wish? I know when I was starting out, I think patience is a key virtue to have in this. Like, I find young people today are very in a rush to like keep going forward. And I think it's through the eagerness of wanting to do cooler and cooler things. I think expertise takes a lot of time, and this area is very complex. I always say, if you were to buy a cell phone, would you build your own? Like no, you wouldn't. Building a cell phone is extremely complex, and there's a barrier to entry because you need physical hardware labs and chemistry labs and electronics labs to build a cell phone. So the barrier to entry is very difficult. But I'd say building AI software is just as complex as building a cell phone, but the barrier to entry is a lot lower because anybody can open up an open source window on their laptop or open up Excel and put in some math equations, and that barrier to get in is very low. So to develop expertise, though, takes a long time. Like, if you read Malcolm Gladwell's book Outliers, it takes 5,000 hours to have some level of expertise at anything. So 5,000 hours, that's like at least 2 years full time, 24 hours a day, 300, like 220 times 8 is 1,600 hours. That's like, I think 2,200 hours, I remember from consulting days, as kind of a consulting year. So it takes at least 2 to 3 years at doing something to build some level of expertise. And so I think having patience and having perseverance, I think those are important things. So, try something out, give it a real go. I think don't hop around too much. Obviously, when you're young, it's a great opportunity to find out what you like, but don't be overly in a rush. Um, to evolve too quickly, because then I think if you don't spend the time in any one type of job, you will never develop the expertise in that area. And if your objective is to be an expert, then you should be patient and spend a lot more time in one place, learn as much as you can before you move out and do something else. So the greatest skill you come out of school with is the ability to learn. And I think when I look at university degrees on resumes, I think that's a statement that the person who achieved that objective has the ability to learn. And I think I would always rather hire someone who shows a creative spark and interest and curiosity, who wants to learn more, than someone who sits back and say, I have these skills and that's it, right? So I think lifelong learning is key. I think it's impossible to stay abreast of everything, but certainly, I've continued to read academic papers and continue to show an interest, as I love this field, given me an outlet to apply my technical skills. So I continue to read the literature as it relates to the Daisy work that we do. Also, in just general areas of interest, my graduate degree was in turbulence modeling, so I still read aerospace papers because that's interest and that keeps my creative juices flowing. So part of the job should be on the job learning. Stay abreast, read the lay literature that's out there, a bit of the media, some kind of semi-technical writing, and then I read academic papers from certain researchers, and I attend seminars and courses. I've gone to machine learning summer school and Iceland. I went to one of those. They have them in different parts of the world, and they had a big data boot camp in Toronto at the Fields Institute. So I went to that 1 year, and so I think finding opportunities for that continuing education, or taking continuing education programs in universities, or sitting in on lectures. I mean, if Jeffrey Hinton was lecturing at U of T, I mean, I would have, I sat in on his lectures, because I found it fascinating. So auditing courses, and now with a lot of the open university stuff, I'm a physics nut, so I, watch all of Leonard Susskind's physics lectures. I've watched a whole series of, like, I don't know, he's got like 50 of them or something. I've watched all of those. So I absorb all the available sources to keep learning. And I would suggest that people do that. And you don't have to learn broadly. You could pick the areas that you're interested in, or if you see something at work or whatever that is. But lifelong learning, I think, is the best skill that you can bring to any career, not just that career in AI. Where do we see AI going over the next several decades? I think there'll be more and more, I think, narrow applications of AI. I think we need to focus on solving specific problems. And there are lots of companies who are solving specific problems with AI. I think what we'll see more systems thinking being brought to the bear, like I talked about, control, stability, fault tolerance, as these systems become more widely used. We'll start to ask those questions. How do we make sure it doesn't make mistakes? How do we make sure it doesn't crash and fail? How do we make sure that it's repeatable and stable? And so I think a lot of evolution there. I think so. I think a lot of that thing. Then there'll be a lot more figuring out how human beings interact with the technology. Because we don't want to wholesale replace people. I think that's not the objective of anybody. But I think that, so I think there'll be a lot of evolution in figuring out how does an AI system interact with people, and what's the right role of people and technology. So I think there'll be a lot of evolution there. And I think the technology will just continue to get more practical. I think a lot of the conversation has been about the technology itself, and not very easily accessible to the lay people and the general business people out there. And I think that's why one of the reasons I'm motivated to do this podcast is to change the conversation a little bit. So I think there'll be more evolution in practical application, human change management. I think there'll be an equal weight spent on that as there is on the technical evolution of the technology itself. So I think we'll see reinforcement learning will dramatically grow. I think already a few years ago, the number of papers written in reinforcement learning is starting to outpace the number of papers written in deep learning, and now we see deep reinforcement learning. And so I think we'll see this more in reinforcement learning. I think is really the next interesting wave, as well as kind of swarm intelligence is something very fascinating. That having intelligent, if you think of like an ant colony, very simple ants. Uh, when they together as a colony display incredible intelligence. Just as a side story, because I like to go on tangents. I remember sitting in a hot tub once, and ants ants will always find the shortest path between 2 points. So if I put a food source on one side of the hot tub, and I was sitting there like for hours, drinking a glass of wine, and I watch these ants, and when ants find a food, they lay a pheromone trail, like animal hormones, and when they find a food source, they lay a stronger pheromone trail, and the ants follow each other's pheromone trails. And if it's a weak pheromone trail, it decays and less ants follow it. But if an ant finds food and lays a strong trail, then all the other ants start following it to go get the food source. And you'll see 10% of ants kind of randomly explore. And so this is one of the biological analogies for algorithms, and like, so ants can like literally solve a complex maze, right? And so yeah, it's interesting tangent. That I don't know how I got on that one, but how that came to mind. Yeah, ant colony optimization. Yeah, so that was the swarm intelligence. That was the thought. How I think that having kind of swarm intelligence as the computing capacity goes up, and maybe in 10 to 20 years, we'll start to see more practical applications of quantum computing. And so bringing even more computing power to bear, I think will make algorithms even more powerful. And so I think those are the developments. And I think we'll get more autonomous systems. I think data science jobs will decline a little bit. I don't think they'll ever go away, but I don't think they'll be as ubiquitous as they seem to be today. I think it'll be more intelligent software, and once that happens, then there'll be a finite number of data science jobs. I think software development and building software, I think, will be a hot area over the coming 20 years. I got some great questions from the first podcast or comments. A couple of them were, around, the AI is overblown. I wouldn't say it's overblown, but I think there's a level of factual completeness which is missing from the conversation. And so it's, when I made some comments about the leaders in the field, being factually honest, not to suggest that any of them are lying, and I'm sure they're all trying to tell their story, but I think the facts are not getting completely out because of the nature of 30-second soundbite media. I think we want factual completeness. And I think it's important for two reasons. One is for the lay people. I mean, I spoke at a women's insurance conference recently, and somebody asked questions about AI, and I tried to give a balanced view about my opinions about AI. And a few people came up to me after saying, they felt kind of a little bit more relieved and not so scared. So I think, well, that behooves all of us in the industry, I think, to try to be factually complete. Now, I'm sure everyone is trying to be factually honest, and I wouldn't suggest anyone's out there lying, but I would say factually complete is important and tell the whole story. One other comment was around autonomous. As I said, kind of Daisy's mission is to elevate people. And so, the statement autonomous, when somebody said, well, isn't that against the DAISY mission? You're trying to elevate people. Then you say autonomous. Autonomous sounds like you're getting rid of people. And so, well, no, I guess the clarification would be that the technology is autonomous, that the software runs on its own, the autonomous technology, but then human business processes is the integration of people with autonomous technology. So it's not that the technology replaces the people, but the technology is a self-contained unit. It's a system that can run autonomously, and the human interaction with that system is there's still a human interface. And so we're just elevating the role of the human to be the boss of the AI. The human always has the kill switch or the ability to say, I agree, I don't agree. And so that's just a clarification on what I meant by autonomous. And autonomous was more a reference to the technology, certainly not to the human business processes and human technology interaction. Thanks so much for tuning in. I appreciate, hopefully, some of the advice or stories that I told. You can find some motivation in that, or find some learning, and it'll help you if you're looking at careers in this industry. Feel free to like or subscribe to the podcast. That always helps to get the story out. And feel free to ask questions. If you want to be a guest on the show, just reach out if you have questions or comments. If you like what I said, don't like what I said, agree, disagree, that's great. If there's great questions, I'll always try to follow up in the next episode to answer some of those questions. Always happy to help out in any way that I can. So thanks again.